This third and final example for 7.3 day 1 is going to be another kind of long one again, but this time we're going to solve the system represented in a slightly different way, and that is an augmented matrix. We have two columns here. One is a system of equations, one is an augmented matrix. They represent the same thing, and I want you to notice here that an augmented matrix is really just taking the x's and y's and the equal signs out of there, taking all the extra junk out just to leave the numbers, which is really what we're trying to work with anyway. So you'll notice that we have x minus 2y plus z equals 7, and that's like saying 1x minus 2y plus 1z equals 7. And so one thing that we're going to do with this is we're going to translate it into a matrix first and then use the matrix to solve the system. The overall goal, like we had in the very first example, was to get a triangular form and do back substitution. With a matrix, that's going to be what we call row echelon form. That's when there are ones running down the diagonal and all zeros down below. So if there's nothing there, we are going to write a 0. But this is the goal in row echelon form, to get our matrix to look like this. So we will now go into the example. Here is the example. We're going to solve this system of equations. And we're going to do this by first of all converting that to a matrix. So converting it to a matrix looks like this. It's an augmented matrix. And again, this is x, y, z. And this is just what it's equal to. This is the right side of the equal sign in this case. So we've got our augmented matrix. Now what we're going to do with that is go about our normal row operations like we did in the very first example. We want to eliminate the lower x's first. Once we've gotten rid of those, then we'll eliminate the lower y. Then we'll hopefully be in our triangular form or our row echelon form in terms of a matrix, and then we can keep moving along. Now, one operation that I mentioned was kind of an optional thing in the first example, but it's actually going to come in more handy here, is that we can switch two equations. I think it's a good idea to switch row 1 and row 2 because if you have a 1 in this first position, it's a little easier to do the eliminations along the way. So I would say here we switch row 1 and row 2. We switch row 1 and row 2, that puts the 1 right up there. Now we're going to try to eliminate those numbers. So next step then is to do just that. We want to eliminate the 3 and the 4. Now in the very first problem we did in this section, I did just one row operation at a time. I'm going to combine things a little bit here because I think that you'll probably be able to limit your space a little bit more. So here are the two row operations that we're going to do. We're going to start with -3 row 1 plus row 2 is a new row 2 because I want to eliminate this 3, multiply this row by -3. So that is going to come up here. Alright, so we have then -3, -6, 9, and -36, just multiplying all these by -3, and then we're going to bring this one up beside it, 3, 7, -11, and 44. We add those two together, gives us 0. We do actually want to write the 0 in there because this is a matrix. And then 1, -2, and 8. This will be our new row 2. Now let's do the third row. We want to eliminate this 4 as well. We are going to borrow from the first row. We're going to do -4 row 1 plus row 3 is a new row 3. So we are going to use this one up here, bring that down, and we're going to add it to this one. So if we do that, we get -4, -8, 12, and -48. Add that to our current row 3, 4, 9, -13, and 53. If we put those together, we get 0, 1, negative 1, and 5. All right, now that we have this, we're going to replace, oh, and by the way, this is row 3. So now we'll just do both of those replacements here, and we'll get this as our new system. That's what we replaced it with. So at this point, we have both of the x's eliminated. Our next goal is going to be to eliminate this y. So if we're going to eliminate this y value, we want to use row 2 to do that, since we already know that the x's are out of the picture. If we use the x's, since they're out of the picture, then we won't reintroduce an x into this problem, and that's a good thing. So what that's going to mean here is negative 1 row 2 plus row 3 is going to be our new row 3. So I'm just going to do that within here because it's not too bad. This, we change those all to their opposites. We add those together, and it's going to give us 0, 0, 1, and negative 3. And then we can replace that. That's now going to be our new row 3, putting us at this point in the process. Now we have all those ones going down the diagonal. This is called row echelon form. We're ready to solve this thing. This is where we're at back substitution. Now, with back substitution, you can either think of it in terms of the matrix, or you can rewrite it back into a system of equations if that's a little easier for you. So if we do that, you'll notice that z is equal to negative 3. We can plug that into the second equation. So y minus 2 times negative 3 equals 8. So that's y plus 6 equals 8, making y 2. Then we can plug the 2 and the negative 3 into the first equation. We get x plus 2 times 2 minus 3 times negative 3 equals 12, which is going to mean that x plus 13 equals 12. Subtract 13, x equals negative 1. That's our third value. And so finally we can put this into an ordered triple where it's negative 1, 2, negative 3 for x, y, z. If you're ever not sure if you've got the right solution, you can always feel free to go back and plug it into the original equation. If we go back to the original equation on this one, it's all the way back here to this. So if you're confident, maybe you don't need to do that, but if you're ever in doubt, feel free to plug it back into the original.